This is a cyclone. It's one of several that hit Bangladesh every year. When cyclones hit land, energy is released with devastating effects. Like all of our weather phenomena, cyclones occur because a particular set of conditions come together in the same place at the same time. In the case of cyclones, one of the key conditions is the amount of energy that's available, and that's determined by climate. Like a giant energy bank, climate provides the background conditions that in turn shape patterns of weather, determine long-term average temperatures on land and sea, influence ocean currents, and even dictate which plants and animals evolve in ecosystems. There's a great deal of evidence to say that global climate is changing, but those changes aren't occurring at the same rate everywhere on Earth. And that means while some areas are experiencing dramatic changes, elsewhere there are barely any changes at all. The biggest single factor affecting climate is the amount of the sun's energy that's retained by the Earth and its atmosphere. Right now, levels are on the rise. The sun's energy isn't getting any greater, but how it's retained in the Earth's atmosphere is changing. And that means there's more energy available to melt snow and ice, move water around in the oceans, and drive weather systems. Finding evidence to support the idea that climate change is taking place now and in the past is actually quite difficult, but it's not impossible. Because they respond slowly to long-term variations in temperature, glaciers and ice sheets are one of the main sources of evidence helping researchers understand how the world's climate is changing. Dr. Matthew Roberts collects evidence about climate change by monitoring the advance and retreat of glaciers. Right now, he's working on the Sólheima Jökull Glacier in Iceland, measuring how much ice is melting. Glaciologists call it ablation, which is why the device he's using is called an ablation stake.
A strange device with a steel wire connected to it, extending into the ice surface, is used to measure ablation rates, the amount of vertical melting that's taking place at the ice surface. And typically in this sort of area, melting rates are between 8 and 10 meters per year.
If climate's changing, melting should be increasing or decreasing, causing the glacier to advance or retreat. So as well as calculating changes in the volume of ice, Matthew also measures the distance from what's known as the tip or snout of the glacier to a fixed point. The same measurements are repeated at other glaciers in Iceland. And as the red areas of this graph show, for most of the last 100 years, increased temperatures mean Iceland's glaciers have been in retreat.
When they started this in the 1930s, and this picture shows this here, retreat basically is red, advance is blue, and in the 1930s when they started, most glaciers were retreating. But in the 70s, glaciers started to advance again. And now basically, most monitored glaciers are retreating. And that has been the signal. So over the last century, you could say the signal is that glaciers have been retreating a lot.
But advance and retreat aren't the only way glaciers provide sources of evidence of climate change. 1,000 kilometers to the northwest, researchers in Greenland are using global positioning system technology to record the speed at which the ice sheet is flowing into the sea.
And we're on a pretty massive block. It stretches back 20 kilometers. And what we're doing here is putting some fancy, fairly elaborate GPS systems on this block, monitoring its movement. So we're looking on a minute-by-minute basis on what it's doing, how it's moving in relation to the rest of the glacier, and looking for that critical point where it fractures and breaks off.
Greenland's ice sheet contains nearly 10% of the world's glacial ice. And when that ice meets the sea, it produces nearly all the icebergs in the North Atlantic. It also means the speed at which the ice melts has a direct impact on global sea levels. As well as monitoring its retreat, Researchers on the Jakobshavn Glacier have shown that the speed at which it moves has doubled. It's now around 2 meters per day. Rising sea temperatures provide further evidence of climate change and are helping to accelerate glacial melting. But while the changing extent and flow of glaciers gives us recent evidence that suggests our climate's changing, climate has in fact changed over much longer periods of time. These trees are part of the world's largest mangrove forest in the Sundarban in southern Bangladesh. It's one of the most diverse ecosystems on the planet, and as well as supporting thousands of species of plants, insects and birds, it's also home to the Bengal tiger. The reason the forest ecosystem has evolved here is because, like all plants, mangroves thrive in particular conditions. And because climate influences long-term average temperatures and weather patterns, it's one of the factors that have enabled them to thrive. It's also why climate influences the nature of the ecosystems over a much larger scale, creating larger zones or biomes with similar types of ecosystems. Based on the links between climate and vegetation, in 1884, climatologist Vladimir Koppen divided the world into 5 distinct zones, or biomes: tropical, arid, temperate, continental, and polar and alpine. By looking at fossilized plant remains, or pollen, trapped in ice that's thousands or millions of years old, researchers are able to see how the vegetation and climate have been changing for millions of years. But when it comes to finding evidence for more recent changes, one of the best ways is to look at global temperatures. For hundreds of years, weather stations around the world have been taking daily temperature readings. By taking averages of these temperatures over several years, you can turn them from weather readings into climate data. And when researchers crunched the numbers, they found the evidence suggested that for most of the last century, average temperatures increased steadily. But when it comes to collecting evidence about changing global temperatures, the biggest advances came with the development of satellite technology. By measuring infrared emissions, sensors on board these satellites are able to provide accurate readings of land and sea surface temperatures. And when this data is combined with average readings from weather stations, it soon became apparent that temperature rises vary enormously across the globe.
Basically, if you look at this, it turns out that the southern hemisphere actually hasn't been warming very much in the last 20 years or so. But the tropics have been warming. And then if you look at the northern hemisphere, it's been warming quite substantially. But if you add the Arctic, you have to change the scale. And this red line here shows you the Arctic. And now you have to go from -1 to +1. And the other lines just appear like they're all bunched together here, and because the Arctic has been warming quite rapidly in comparison.
Satellites can also measure annual variations in ice cover and the movement of tiny particles in the atmosphere, both of which have important effects on climate. And by combining this information with evidence from glaciers and land-based weather stations, there's absolutely no doubt that the Earth's climate is changing. But 2 big questions remain. First, how much of this change is due to natural causes? And second, how much is the result of human activity? These days, anyone wanting to walk on the surface of the glacier at the Mer de Glace near Chamonix in France has to climb down an awful lot of ladders. But if you'd have stood here 20,000 years ago, you'd have had a kilometre of ice above your head. The massive difference in ice levels are the result of changes in climate.
Well, climate changes on all sorts of timescales for a variety of reasons. Climate changes naturally, and it's changed naturally for thousands and thousands of years, and that's related to a number of factors, including the fact the output from the sun varies, including the fact that occasionally we have large volcanic eruptions that put dust way up into the atmosphere, and that cools the climate. And it's changed also because we have natural oscillations of the climate system, and the most famous of those is called the ENSO, the El Nino Southern Oscillation, and that's related to variability of temperatures in the ocean, in the Pacific Ocean in particular, and that affects global weather patterns. But we're also seeing climate changing now outside the range that we've seen before from natural factors, and that's because of greenhouse gas emissions into the atmosphere.
To understand why climate changes, we need to look at what causes fluctuations in the amount of energy reaching and being retained by the Earth and its atmosphere, or what's called the Earth's energy balance. The energy that warms our planet comes from two sources. Light from the sun, or solar radiation, is overwhelmingly the greatest source, but some is contributed by volcanic activity. Stand a few meters from a lava lake and you can't help but be amazed by the amount of energy being given off. It might seem impressive, but on a global scale, the amount of energy given off by volcanoes is relatively small. Unlike this one, most volcanoes don't erupt very often. Put these two factors together, and it means although they can have some impacts on climate, they don't really affect it over long periods of time, especially when compared to the amount of energy that comes from the sun. Every second, the giant ball of fire at the center of our universe emits 1 million times more energy than the United States consumes in an entire year. And it's that solar energy that drives the climate. Sunspots and solar flares can affect the amount of energy given off by the sun. But by the time they reach the Earth, these variations have relatively little impact on climate. In fact, satellite data show that although the last decade has been one of the warmest on record, the output from the sun has actually been in a bit of a lull. It also means global temperatures are rising because changes on the Earth's surface and its atmosphere are causing more solar radiation to be retained. About 30% of incoming solar radiation is reflected straight back out to space. Brighter surfaces like ice caps and sheets are the most reflective zones, whilst darker land surfaces, such as forests, absorb much more. This means that if glaciers melt and expose darker surfaces, more energy gets absorbed, and that can raise temperatures even further. It's also why the amount of seasonal Arctic sea ice plays a crucial role in regulating the Earth's temperature. Summer ice cover has been decreasing for the last few decades and hit a record low in 2012. New navigable routes have already opened, and some researchers predict the Arctic could be ice-free in summer by the end of the century. But it's not just the Earth's surface that affects how much solar energy gets absorbed. Some of the incoming energy is reflected by tiny particles in the atmosphere called aerosols. Natural aerosols include fine-grained sand and dust, salt particles produced when waves break, and smoke and ash from fires and volcanoes. But whenever they burn anything, people create aerosols too. Billions of car engines, power stations, and open fires are constantly pumping massive amounts of aerosols into the air. And because they move around in the atmosphere, the impact of aerosols is hard to assess. It's made even more complicated because while some aerosols reflect incoming radiation, others absorb it. But whether they're natural or man-made, reflective or absorbent, the biggest impact aerosols have on climate is because they affect cloud formation. And because clouds reflect a lot of incoming radiation, they really can change the Earth's energy balance. Some researchers believe that clouds will act as a braking mechanism, slowing global warming. They say that if the Earth's temperature rises, the amount of evaporation will increase, and more clouds will form, increasing reflection and reducing the amount of energy reaching the surface. It might sound great, but unfortunately, most climatologists say it's not that simple. Although clouds reflect incoming solar radiation, the water vapor they contain is what's called a greenhouse gas. Like the glass panels in a greenhouse, this vapor prevents energy radiated from the Earth's surface being lost back into space. But water vapor is just one of many different greenhouse gases, and the biggest impact people have on climate is because we produce a lot of them too. Burning fossil fuels like petrol, gas or coal creates carbon dioxide, sulfur dioxide and nitrogen oxides, all of which are greenhouse gases. They prevent heat from the Earth's surface being radiated back into space, creating what climatologists call an enhanced greenhouse effect. And it's not just fossil fuels that create greenhouse gases. Animal dung and rotting waste on rubbish tips produce methane. Over the next 20 years, this greenhouse gas will trap heat 72 times more effectively than the same volume of carbon dioxide. And as this table shows, there are others too. It's no surprise that when you put them together, the enhanced greenhouse effect is already having impacts all around the world.
Because of the extra greenhouse gases that we've emitted into the atmosphere, that's added to the greenhouse effect, warmed up temperatures in the atmosphere, also warmed up temperatures of the ocean, which meant that the ocean has been expanding. So sea level's been rising at about 3 millimeters per year. And it's also meant that the snow and ice is melting. So the Arctic sea ice extent is reducing. And we're seeing that globally rainfall patterns are changing. And basically what that's meaning is that the areas that have more rainfall naturally are getting more rain and more prone to flooding. And the drier areas of the Earth have been getting less rain. So therefore that's having an impact on agriculture globally.
Researchers and politicians might argue about the causes, but whether it's due to natural changes or human emissions, our climate is changing. And for the last 30 years, our planet's been getting warmer. And nowhere is that warming been greater than in the Arctic. In 3 decades, the amount of summer sea ice in the Arctic has decreased by about 750,000 square kilometers, reducing the amount of habitat available for polar bears, seals and other ice-dependent creatures. Further south in Iceland, increased temperatures on sea and land have also begun to affect movements of fish stocks and migratory birds.
There are some new birds that come in. We also have birds that leave. So some seabirds in Iceland that are cold adapted. Iceland has now become too warm for them. But so we lose some and we get some instead. In the ocean, there have been huge changes especially in migratory fish stocks. Capelin changed its behavior substantially around the turn of the century. Some of that is sort of coming back. But you know, that's a very clear example of warming having an impact.
But rising temperatures and melting ice aren't just affecting Iceland's fishing industry. It might look cold, but Iceland's long-term average temperatures are rising, and that's likely to have long-term impacts on the country's ability to generate power, or its energy security. 70% of Iceland's electricity comes from hydroelectric power, or HEP. It's generated using glacial meltwater to drive massive turbines which produce electricity. But if the Met Office's computer model is right, over the next 200 years, the amount of meltwater available could change dramatically.
you go from a system that looks like this, okay? And in about the space of 200 years, and now we go really fast, it goes like this. And so you go from this to this quite quickly. Well, in a geological sense, this is very, very fast, even though it may be several lifespans. This is quite substantial. And this is a huge change. You know, there's a lot of areas that used to be glaciated, which will open up. There's rivers that will form, rivers that will change course, and so this is a big environmental change. And for a country called Iceland in 200 years to have no glaciers, that's a bit odd, isn't it?
But it's not all bad news. For the next 30 to 50 years, Iceland's electricity companies are hoping to take advantage of increased meltwater and generating capacity. They're even looking at the possibility of laying a cable to Scotland and selling electricity to Europe. But elsewhere in the world, the impacts of glacial melting are potentially much more serious. In Tajikistan, rising temperatures are causing glaciers to melt and retreat at unprecedented rates. Since 1927, this glacier above the Zarafashan Valley has retreated by nearly 4 kilometers. It's not just creating problems now, but also for the future.
Последующие 20-30 лет будет наблюдаться увеличение водности в реке и увеличение возникновения стихийных бедствий, связанных с водой. Потом, после 20-30 лет, будет наблюдаться резкое сокращение водности рек.
The combination of massive quantities of meltwater and intense spring rains mean mudslides and flash flooding have become increasingly common. This village used to be home to 250 families, but repeated mudslides mean many people have been forced to move away.
aynı zamanda همه قشلاق و 54 خوجی زندگی میکند. این حادثه همه وقت خلقا گمانبر هستند که بارون که گرفت البته میآید. برای همین بسیاری خانه ها نزدیک سیلگاه و قد راه سیلبا وقتی که بارون سخت میبارد خلقا واهمه میغلطند که
Tajikistan is Central Asia's poorest country. Even before the predicted fall in river levels arrives, access to drinking water is limited. For most people in the area, the only reliable supplies are the boreholes funded by development agencies. Farmers like Haitboy Karadov are likely to be the worst affected. Already living on the poverty line, he simply doesn't have the resources to adapt to the changes. And rising temperatures and ice melt are likely to affect billions of people around the world because they impact on sea levels. As temperatures increase, especially in Greenland and the Arctic, glaciers and ice sheets like Kangerluthak are both retreating and moving faster, releasing massive amounts of ice into the ocean. And as the icebergs that form break up and melt, the amount of water in the world's seas is steadily increasing. It might sound like a doomsday scenario, but rising sea levels aren't a new phenomena.
We know that sea level globally is rising. It rose by about 19 centimeters in the last century. And there are projections of the rise up to about 1 meter in the next century, ranging from 50 centimeters to 1 meter. There's a lot of errors in that, a lot of uncertainty in that. The problem with the uncertainty is not just physical things, how will the sea react and so on. We don't know how much we're going to emit. So that means we don't know how much it's going to warm, and that means we don't know how the sea level will respond.
Despite all the ice melting into the oceans, the greenhouse effect means sea temperatures are also on the rise. That causes the water in the oceans to expand, adding a few more millimeters to the level of of the increase. This map shows the areas that would be impacted by a metre of sea level rise. But the latest research suggests that changes in levels will vary around the globe.
Greenland, like any other massive body, it has a huge amount of mass, so it attracts other mass towards it. And the mass that is most easily attracted is the ocean. So it actually keeps the sea level higher, close to Greenland. Now, if you take the ice away, then this effect is diminished and the sea level drops. That, of course, means it will rise more somewhere else, but somewhere else is actually 2,000 kilometers away.
As with predictions for sea level rise, there's a lot of uncertainty about which areas will experience the biggest changes. But whatever happens, the impacts will depend on the resources people have available to adapt to any changes. This is called their resilience. And one area where poverty and a fragile environment mean even small changes are likely to have a major effect are the mangrove forests in the Sundarban in southern Bangladesh. These spikes are the upper part of mangrove roots. They're an adaptation that enables mangroves to live in what's called the intertidal zone, the area between high and low tide. Another reason mangroves thrive here is because they're able to deal with levels of salt in the water that would kill many other plant species. The mangrove's roots trap sediments, twigs, leaf litter, and all sorts of other debris from the forest. Over thousands of years, so much organic matter has built up in the Sundarban that together with the Amazon, it has become one of the most important carbon stores on the planet. This carbon also provides the first link in the Sundarban's food chain. And for millions of years, its riches have created a platform enabling diverse species to evolve. Without the carbon held in the mangroves, the Royal Bengal tiger wouldn't be here. And because the mangroves act as a bridge between land, estuary, and sea, the Sundarban has become one of the most important, diverse ecosystems in southern Asia. But climate change and rising sea levels could soon change all that.
Mangroves in the past, geologically, have adapted to sea level rise before. And so their ability to adapt to climate change, it all depends on how fast climate change is actually going to happen. Because in the past, rates have been quite slow. And as sea level has risen in the past, mangroves have been able to actually build up in time with that sea level rise. But what will happen now, we're not sure actually of the rate that sea level will rise. So depending on that rate, the mangroves may persist or they might be drowned.
If the mangroves go into decline, all sorts of other species, from trees to shrimp larvae and dolphins, will be affected. For over 1 million fishermen, shrimp farmers and rice growers living on the low-lying coastal fringe, changing sea levels are likely not just to lead to an increased risk of flooding, they'll also take away people's means of making a living. But rising sea levels aren't the only way that Bangladeshis are likely to be affected by climate change. On the 25th of May 2009, Cyclone Isla hit southern Bangladesh. Overnight, it flooded and destroyed the homes of 750,000 people. Sanitation systems collapsed and widespread flooding contaminated fresh water supplies. In all, this single storm affected more than 3.5 million of the world's poorest people. And current research suggests that if climate change continues, severe events like this could become more frequent.
So our understanding as it stands at the moment is that the sea surface temperatures are rising, and there's a very clear link between increasing temperatures of the oceans and what we've been doing to the climate through emissions of greenhouse gases. And that is having a tendency to make more intense tropical cyclones. And the climate models in the future project an increasing frequency of the most intense tropical cyclones.
Like all cyclones, Isla began as a tropical thunderstorm. These form when intense heating of warm, humid air causes updrafts, resulting in the formation of tall cumulonimbus clouds associated with extremely heavy rain. To turn into cyclones, tropical thunderstorms need a continual supply of energy in the form of warm, moist air. And that's only available where sea temperatures reach 26.5 degrees. It's also why, as this map shows, tropical cyclones, or hurricanes and typhoons, can only form in a narrow band, 10 degrees either side of the equator. And if global sea temperatures increase, the conditions tropical cyclones need to form are going to become much more common. But climate change is also affecting weather patterns in other ways, and the impacts aren't always negative. Olafur Eggertsson is pressing oil from rapeseed grown on his farm in southern Iceland. His family have been farming sheep and cattle here for 5 generations. But changes in climate have enabled him to grow rapeseed commercially for the first time. And that's not the only way crops in Iceland are changing.
With warmer climates, of course, there are some things that you can grow that were harder to grow. And in the last decades, grain production has increased in Iceland quite substantially. So that is a response to the warming, basically.
Climate change might be helping farmers like Olafur to diversify, but in other parts of the world, the impacts are very different. And it's the least resilient communities that are usually hit the hardest.
Climate is affecting different parts of the world differently. Potentially even, it may in some regions be easier to grow crops, for example, in some parts of the world, potentially at least, but in other parts of the world, particularly like regions already prone to drought, are getting more prone to drought, and therefore it's becoming then much more challenging to have enough water. And one of the unfortunate consequences of climate change really is that those places that are already most vulnerable to weather under climate change, because it's changing the weather, they're the ones being affected most.
In recent decades, droughts have become increasingly common in East Africa.
In the last major rainy season, this area received rain only for 5 days. So the ponds are not storing enough water, not enough pasture is growing, and the crops are failing. If the natural resource is not doing good, the livestock cannot survive. And if the livestock cannot do good, the people cannot survive.
In 2010-11, 2 rainy seasons failed in a row, and research by the UK Met Office says the failure of these rains was due to the impacts of greenhouse gases and other human factors on climate. To reach this conclusion, the research team produced 2 model worlds, looking at the likelihood of rains failing with different climatic conditions.
Firstly, we have to look at simulations of what the weather would look like between the world that we have now, the one that has been already changed by climate change, and the one that we would expect to have had we not been emitting greenhouse gases and other things since 1750 or whenever we started doing it.
Trying to model what weather patterns would have been like without the effect of humans on climate is extremely complex. But one of the key relationships the model took into account was the link between ocean temperatures and atmospheric circulation.
We have a data set here at the Met Office that measures the temperature of the oceans. So we have that data here, which is the observed temperatures that we saw in the real world in those seasons. The bottom row is the temperature difference you would have to subtract from here to remove the human influence from these ocean temperatures.
It might sound complicated, but the logic is simple. If people hadn't been creating greenhouse gases, the ocean temperatures would have been significantly less, and that, in turn, would have affected atmospheric circulation and weather patterns, reducing the chances of the rains failing. But the impacts of global warming on weather patterns vary across the world.
Global warming doesn't necessarily mean everyone's going to get warmer. And it doesn't necessarily mean that everyone's going to get drier or wetter. There will be a mixture and there'll be an overall shift, but it will provoke lots of little disturbances all over the place. It'll change circulations and it'll change weather patterns. And of course, that's very complicated.
The findings may not help people dealing with drought now, but showing there's a link between human-induced climate change and the East African drought adds to the growing body of evidence. And that shapes how individuals, communities and governments respond.